Well, Harold, I want to start off by thanking you for the introduction there, and also thanking yourself and the rest of the EnerGIS committee for putting this event together here today. Very much appreciate the opportunity to represent Ayres and speak on some of the work we're doing with remote sensing as it pertains to unmanned airborne LiDAR and imagery. And the focus of my presentation today will be on geospatial applications for electric utilities. So I'll go ahead and get started here. Just a brief look at the agenda for today. A couple of the different topics that I'm going to run through here. I'll try to touch on these at a kind of high level. I think a lot of these could actually be presentations in themselves. And then hopefully at the end here, we'll have some time for questions as well. I always like to put this slide in here just to give everyone kind of an overview of Ayres as a whole. We are an employee-owned multidisciplinary engineering and consulting firm with a fairly diverse range of services. For the purposes of this presentation, I will just stay focused on the geospatial side of the house. So Ayres Geospatial, just to provide a brief overview on that, we are a nationwide end-to-end geospatial solutions provider. Primarily for us, that encompasses survey, aerial mapping, and GIS. Fairly experienced here with aerial, mobile, terrestrial, LiDAR, and imagery processing for a really variety of clients and project types and deliverables. We are actually one of the longest standing photogrammetry divisions in the US that still practices true photogrammetry to this day. Very involved as well in the ASPRS, multiple certified photogrammetrists, certified mapping scientists, and mapping technologists in LiDAR, as well as CMSs in GIS, LIS, and several GISPs on staff. At this point in time, we're licensed to perform survey work in about 15 states, with new licensure for various states coming on all the time here. So as far as it pertains to LiDAR and imagery, I'm not very sure among the audience as far as the level of familiarity with LiDAR and photogrammetry. So I did want to touch on that as a starting point and give or set something of a baseline here. So I'll start with LiDAR. LiDAR stands for light detection and ranging. It can be airborne, mobile, terrestrial as far as the platform for acquisition. It is an active sensor technology. So the laser scanner itself is generating its own light source. And that does provide actually a pretty big advantage to how you can acquire data with it. It is also random sampling. And when I say that, what I mean is that if we have a 1 meter by 1 meter target on the ground, depending on the scanner, the scan settings, the height, and the speed of collection, we can be fairly confident that we're going to hit that target. We just can't state, where exactly on that target are we actually going to hit. And then most sensors these days are capable of multiple returns per outgoing pulse. And this leads me to, 3 of the key advantages I want to point out when it comes to LiDAR. The first is that because it's active sensor technology, it is agnostic as to when we can go out and collect data. So we can collect day or night, which really does provide flexibility, especially in these dense urban areas when we're trying to use UAS technology. If there's no imagery component to the project, then this is a suitable approach for us to take. The other key advantage, you're able to penetrate down through vegetation. The rule of thumb with this really is if you're standing in a forested or canopied area and you look up and you can see sunlight coming down through the canopy, you're probably going to have a pretty good chance then of getting returns off the ground surface itself. And the last one, and this comes into play with some of the transmission distribution mapping work, is we're getting very dense data with very high fidelity of features. So that's a really good advantage for us as well. And then just briefly to touch on photogrammetry. Photogrammetry is overlapping images that are used to create maps for essentially the purposes of making measurements. Unlike LiDAR, it is a passive sensor technology. It does rely on external lighting conditions. And as a part of that, we do need to be cognizant about having optimal lighting conditions during acquisition, keeping track of sun angles during the year and even cloud cover during the time of acquisition. It is a better suited technology for bare earth sites with minimal to no vegetation. And the overall feature extraction process from photogrammetry is much more manual than it is really from a LiDAR perspective. Even with these, what really could be looked at as limitations of the technology, it really doesn't mean that photogrammetry is obsolete. It can actually be an extremely cost-effective approach for a bare earth site with little or no obstruction of the ground surface. So, and I think, we talk a little bit about LiDAR and photogrammetry and some of the advantages and maybe disadvantages depending on how you look at it. And the question that usually comes from that is, well, which one should I use for my project? And the answer really is it depends. And we need to understand a couple things going into that. The first is, what kind of site conditions are we dealing with? What are the features of interest that we're looking at potentially extracting from a data set? What kind of deliverables are we going to be providing to a client? And what are some of the project specifications and the required accuracies that we're trying to hit? And really all of this is to say that what we try to focus on doing here at Ayres is taking a solutions-based approach, understanding these different considerations, and then trying to identify whether LiDAR or photogrammetry, and between those two, which platform is going to make the most sense for that kind of a project. One of the key advantages, and a lot of more modern systems do have this now, is a simultaneous dual collection of LiDAR and imagery. It's a really cost-effective way to collect dual data sets, so imagery and LiDAR at the same time, so you can meet multiple project needs in a single acquisition. And the closing point I would say on this, LiDAR and photogrammetry certainly do compete in some respects, but they are very much complementary data sets to each other. So I think that's important to keep in mind as well. Before we jump into any of the applications and some of the sensors that are out there, I do want to quickly touch on LiDAR versus dense image matching. And the reason I want to touch on this, there's a bit of a misconception around these two. Let me start by defining dense image matching. So dense image matching is a photogrammetrically derived point cloud. Typically that's done using an off-the-shelf software, something like Pix4D or even Agisoft Metashape. The misconception that I think that we've been seeing a little bit here is that dense image matching and LiDAR point clouds are equivalent in all respects. And really that's not the case. Your dense image matching point clouds are going to struggle more around any kind of above ground feature or through any kind of vegetation. And under the proper conditions, dense image matching definitely can be a very useful and effective tool. But it goes back to those project considerations I mentioned on the previous slide. You really have to think about that stuff as you're looking at these different kinds of projects. And I like to show this. I thought this was just a good example of dense image matching versus a LiDAR point cloud. On the left there, the first thing I'll point out is that is the dense image matching point cloud. What you'll see is the shadows of the trees cast on the ground. You'll notice that those are all leaf off. So this was collected during a leaf off condition. It looks almost like a picture, but really what's going on here is it's colorized according to the RGB value of each pixel. So you kind of get this picture effect, but you'll notice around your above ground features, the houses, through some of the trees, that there are voids in the data set there that it was not able to reconstruct a surface through. And so when you look at the LiDAR point cloud on the right side there, that's a point cloud displayed by intensity. The first thing that kind of jumps out is, the voids that were present in the dense image matching data set are no longer present in the LiDAR point cloud. The LiDAR scanner was able to penetrate down through those features and get returns around the above ground structures and underneath the canopy. The example I'll give here, and just in closing on this, if the objective of your mapping project was to extract the center, top, and bottom of every pole along a right-of-way, dense image matching would probably not be a suitable approach for that. If you run into any areas where there's vegetation encroaching into your structures, really all bets are off at that point about as far as trying to actually extract any center, top, and bottom points off of the pole in that area. So very briefly, I'll talk about some of the UAS sensors and airframes that we utilize. On the top left there is actually a Regal Minivux 2 UAV within a Planix APX-20 IMU. It is hard to see in that picture, but there are actually dual oblique cameras on there. So we are performing simultaneous dual collection. getting LiDAR and imagery in a single pass. And then on the bottom right there is our phase 1 IXM 100 metric camera. Metric is the real important distinguishing factor there. That camera actually is calibrated for use for photogrammetry, but it also doubles as an excellent platform for visual inspections. And I won't go down into all the specs on the sensors. If there are questions about that, certainly I'm happy to answer those after the presentation here. Before jumping into the applications, I just want to touch on some common misconceptions, especially around the use of UAS technology. These were certainly prevalent before. I think as UAS LiDAR and imagery has started to advance and become more popular, they've unfortunately kind of taken off and become more prevalent. The first of those is that UAS technology can replace the need for a surveyor or even boots on the ground. That's not really the case. In fact, the way I look at it, and the way that we try to explain it is really a properly executed project using this technology does require an experienced licensed land surveyor and LiDAR and imagery experts all working together to ensure that the data sets being produced meet established accuracy standards. The other one that kind of is floating around out there is no or little planning is needed. Again, it depends on what you're trying to do. I think if you're looking at, I'll use transmission and distribution as the example here, we really do have to be very careful about how we plan flight lines, not only from the perspective of not having the drone run into the lines or run into a tower, but your offset from that center line is critical to the quality of the data that you're going to collect. So there is a fair amount of planning that does go into these projects. And the other one that's I think is kind of dangerous actually is no or little survey control. Really, we try to have more survey control than less. It really helps us on especially the calibration side of the data, bringing that back down and adjusting it. Beyond even just the survey control, you do need to consider that you're going to need independent check shots for non-vegetated vertical accuracy as well as vegetated vertical accuracy. And finally on this one, there's a bit of an idea around, fully automated pre and post processing. And I'll talk about this a little later here when we get to LiDAR classification, but it's really not, I don't believe completely the case. Certainly AI and machine learning is helping to make processing faster, but I think there'll always be a point of manual intervention here. And, really all of this, I'll just close by saying this, the principles and the science that go into acquiring and processing LiDAR and imagery, that's not really what's changing here. What's actually changing is the method of acquisition, and even that method of acquisition comes with its own considerations. So I'll talk about the first project here. This is actually a circuit mapping for an as-built that we worked on, and we do quite a few of these. What you're seeing here in the video is the tail end of a transmission circuit, and it'll go into a distribution circuit in a moment here. But this was a project for an as-built of 2 circuits. They totaled about 5 miles, and I think there was 3 substations between them. So in this case, we did acquire LiDAR at 60 meters AGL, 5 meters per second. The point density on that is at about 88 points per square meter in a single pass, so fairly dense. One thing I kind of want to point out here, you'll see as it's kind of moving through the video, those individual lines on the ground. Those are actually the scan lines of the scanner. So the way that works is there's a mirror that's rotating 360 degrees as it's moving. We're really only collecting data 60 degrees each side of nadir. So our total field of view is 120 degrees looking downwards. The other thing I do want to point out is you can see we're kind of moving over some distribution structures here. In my opinion, these can be, if you're not careful about how you flight plan this, those can be notoriously difficult to map because they are such a small feature. They're not like a transmission tower, which is pretty tall and has a decent presence to it. So again, you do have to be very careful about how you're flight planning to really collect data that's going to work for your application. So I'll talk very briefly here about some of the deliverables for this. I'll point out just the base ones, the standard ones that we provide. So colorized and classified point cloud, the orthomosaic, and then full meteorological data and metadata in an XML format. Any of the projects we work on related to electric utilities in the transmission distribution space, all of those four are standard across the board. Beyond that point, it really depends on what the client's actually looking for. In this case, we did extract center, top, bottom of pole, all the conductor points of attachment, and then also provided pole tilt. And that data was fed into a PLS CAD file in a back format. And we're not often the ones doing any of the structure modeling or sag sway analysis, but that data does feed into that. And then these are just a couple of screenshots, so I won't spend too long here. Just to give an idea of the pole and wire vectorization and extraction. On the top left, I think that's probably the clearest example. You can see those H-frame poles. They're not always completely upright, or sorry, as far as like being plumb. Sometimes they're leaned over a little bit, so we do have to apply pole tilts. But the two red points on the tops of those poles, that would be your center top of pole. And then it's kind of hard to see because they're a bit behind vegetation there, but the yellow points are actually your center bottom of pole. And then on the image on the bottom, you can see the vectorized wires. You have to look pretty closely, but they are vectorized. And so that would be a data set that's then ready to go into the classification stage. Another project that I thought was unique and I wanted to share here, a clearance study. This was for 2.5 miles of transmission over distribution. I think what happened is they modified, an electric co-op modified some of the distribution structures. And so the electric utility that owned the transmission structure had to then perform a clearance study. But same sort of thing here from a flight perspective. We acquired LiDAR, 60 meters AGL, 5 meters per second. So about 88 points per square meter in a single pass. One of the unique deliverables that we provided from this was actually a bare earth tin surface. Same as the last project, we did provide center, top, bottom of pole, all the conductor points of attachment, and those are usually delivered in a CSV format. I think I didn't mention that earlier, so I do apologize. In this case, if you look at the image on the bottom right there, those are the poles and wires displayed by classification. So you'll see that all the conductors, they're not classified into one class, they're classified separately by phase. That was the important thing there I wanted to point out. And then deliverables, some of those you saw on the last slide. As I mentioned earlier, there are baselines and some of those do repeat. This is one of the applications that I am really excited about. And I know this is a unique one, I think, but LiDAR for vegetation management can be an excellent tool to supplement your vegetation management program. It's a really good way to quickly identify areas of risk that could cause interruptions to power delivery. So you see here, I'm just kind of panning through the point cloud. I'll just explain what you're seeing there. The green points are classified as ground. The white points are all the high vegetation, and then orange is everything that's considered vegetation encroachment. You'll see in a second, I'll move over to view 2 there, and you can get a better look at the poles and the wires from another perspective there. What you'll also notice as I'm panning through, it may be a little hard to see, I think, but some of those red outlines around those encroachment points, those are actually 2D polygons that we can generate, and we can also provide that out in either a shapefile or a KML format. So veg management crews can identify areas that they believe to be of high importance for them to go out and look at and examine trimming. The other advantage here is, what we've been able to do is quantify that vegetation encroachment and actually use that information for budgeting and planning for trim cycles. Now, I'll touch very briefly on visual inspections. From an inspection standpoint, there's the visual side of things and then thermal. Both of those also can be very powerful tools. I won't spend too much time on this, but the image on the far left is actually a substation we're doing an inspection on right now. On the far right, the image over there of that pole, that's a pole taken from a phase 1 camera. I just zoomed in on it. We just had a different perspective of that substation. I thought that was an interesting thing to showcase as well. But really, in my opinion, on this side of things, the future of visual inspections for transmission distribution assets really is going to rely heavily and utilize AI and machine learning. to be able to identify and then flag defects on a much larger scale. And then before we talk about feature extraction and LiDAR classification here, I do want to briefly touch on comparing airborne LiDAR point densities. And so I'll just jump right into it here. But the image on the left of the screen there, that is a dead-end structure. These are not structures from the same project, but they are both dead-end structures collected from airborne platforms. On the left is a dead-end structure collected using our Regal Minivux 2 UAV. And you can very clearly see, the increase in point density, the fidelity of the features. You can actually make out that there's two insulators on either side of the pole. And if you look at the image on the right there, that is a airborne manned collect for LiDAR. And you notice the point density is down quite a bit. It's harder to make out features as far as the conductors. That's really important for us when we're extracting those points of attachment. It helps to be able to see where that actually is. That's not to say that fixed wing airborne or fixed wing airborne LiDAR rather is not inadequate or is inadequate. That's not the case, and that's not what I'm trying to say here. There are varying point densities at which it can be collected, so it very much has its time and place. And I'll talk a little bit here about feature extraction and LiDAR classification. So when we get to the feature extraction standpoint of things, this is really where the high fidelity and density of those point clouds is helpful to us as technicians when we're going in and extracting stuff. So in order for us to actually classify the poles and wires, you could iteratively run macros to eventually narrow down to what you're actually trying to classify. I think that might just be more time consuming, really. So in order for us to correctly classify poles and wires, we first have to actually vectorize and extract them. And a lot of that process now is largely automated when it comes to poles and wires. There definitely is some manual refinement of technicians going in and adjusting the vectorization to more accurately model those features. And typically what we get asked for is more of your center, top, bottom of pole, conductor point of attachment, and then pole tilt, which I think pole tilt can be helpful if you're doing some kind of a storm hardening or pole hardening project. And then looking at LiDAR classification. So unclassified LiDAR is really cool to look at, but it's not actually very helpful to us until we're able to start sorting those points into different classes and actually making sense of what we have there. Typically, there's a lot of off-the-shelf softwares that can do that. TerraScan, Global Mapper, LP360 are all some pretty popular ones. And generally what happens is you will run a macro to start assigning points to various classes that represent features that you yourself are interested in. Macros are great. They'll get you about 90 to 95% of the way there. There's always going to be some level of manual refinement that's involved or manual editing that's involved in that. So that is something to keep in mind. And the last point I'll make on macros is if you're using a macro to ground classify in North Carolina, that same macro is not going to work as well to ground classify in Colorado just because of the sheer differences in the type of terrain that you're dealing with. And I put a couple bullet points here of base classifications when we're working with electric utilities, generally speaking, what we get asked for. And then I do want to just touch on manual editing very briefly. This isn't a UAS project, and I know it's not an electric utility application, but I thought it was just a simpler, easy one to understand and try to convey. So what you can see here is you've got a bridge that's moving across the river, and then the red line on the top right there, that's actually the Google Earth imagery. But you can see that bridge continues back into the woods. And if you look at the image on the bottom left, on the top left of that, you see those orange points, and then I think green or yellow points that are starting to wind through that. So I think what happened here is we ran a ground macro. It didn't pick up the bridge. So then we can look at the surface model that we use as a comparison and see, okay, clearly we missed something here. We need to go back and then investigate. And so we find a bridge, and then we're, as technicians, manually either trying to run a macro or trying to then manually move those points back to the appropriate class. And with that, I'll leave it open for any questions here. I want to thank Harold, everyone at EnerGIS again for the opportunity to present.